Today we are very excited for our April seminar. We'll be looking at 3 speakers, all on the themes of NLP, continual learning. I think this is going to be a wonderful talk for us because continual AI has had a little bit less NLP, especially recently, but we all know that's the talk in the AI world right now. So each speaker today will have 20 minutes total for their talk and questions. And after all 3 speakers have gone, we'll open it up to additional questions and general community discussion. So first up today, we have Jang. Joel is currently an MS student at KAIST, advised by Minjun So, and he's an incoming PhD student at the University of Washington. For the majority of his MS, he worked allowing language models to be ever evolving, and he's currently focused on creating large language models that are completely modular and dynamic. In this short talk, he will briefly introduce his paper, Towards Continual Knowledge Learning of Language Models. This was published last year at iClear 2022. And here he'll tackle and formulate the problem of continual pre-training in large language models. So a very, very important high impact problem that many people are concerned with today. So Joel, I'll go ahead and take it away.
Hi, thanks for having me and thanks for the introduction. I'll just start right away. Large language models are known to encode a lot of world knowledge in its parameters. And this knowledge is known to be gained during the initial pre-training phase, during unsupervised pre-training. And we can probe the language model, giving it like a prompt. Barack Obama was born in, and get the correct answer, Hawaii, in a zero-shot manner. Also, we can fine-tune the pre-trained language model on different downstream tasks that require knowledge. Current paradigms don't really do single fine-tuning, but actually do more instruction tuning and reinforcement learning with human feedback. But this still also requires that the original knowledge is in the parameters of the language model during pre-training. So, for example, if we probe the language models such as T5 and GPT-3, which were originally frozen in 2019, they will output the answer Juventus, which is wrong. The correct answer used to be Manchester United when I first made the slides in 2021. So I asked the same question to ChatGPT just today, and it outputs Manchester United because ChatGPT is frozen in 2021. But I think a good thing is that it does mention that it's outdated, so it knows its limitations. But the correct answer is Al Nassr, which is a soccer team in Saudi Arabia. So this is just a real-world example where even the slides gets outdated. So the real-world knowledge moves very fast. When we probe T5 or GPT-3 knowledge such as blank won the US election 2020, it has no way of correctly knowing the answer. It might have like an educational guess, a forecast guess, like trying to predict the future, but it's frozen in 2019, so it'll never actually know the ground truth answer. So we can divide knowledge and the parameters into 3 different criteria. First is knowledge that should be invariant. So, a place where a person was born, or just some things that should never change. And there are knowledge that should be updated. So it used to know the knowledge, but now it's updated, such as which team a soccer player plays for. And there are these kind of knowledge that are just brand new. So it has never existed in the world, but there is just brand new knowledge. So this is a problem, and maybe one person, like other people, can think that what if we retrieve the updated information? Will it solve the problem? Such as Bing Chat, it augments ChatGPT, which is fully parametric with a search engine. So even though we retrieve the new knowledge and give it as an external prompt to the language model, it still hallucinates, and this has been shown in past works. This is because the language model sometimes has a very hard time when to rely on the knowledge in the parametric space and the external knowledge. So the language model has a hard time deciding when to rely on which factor. So this is still an open-ended problem. And another line of work addressed this problem by doing fine-grained knowledge editing. We in this setting requires tuple X, Y, and A. For example, in the previous example, X might be Cristiano Ronaldo plays for, Y is Manchester United, and A is Al Nassr, a new team. So, however, in this setup, it requires X prime and Y prime, which are neighboring knowledge. For example, different knowledge of Cristiano Ronaldo, because when we edit the model using only this tuple, then it forgets about the previous knowledge about X. And also, this is not a scalable method because we need all the world knowledge in the tuple format, which is very, maybe someone may attempt to do that, but it still requires some fine-grained, some high-quality supervised data. So we can think, how can we update the knowledge and the parameters? So the knowledge was originally gained during continued pre-training, so with the unsupervised pre-training objective. So we can think of continually that pre-training objective on maybe a new corpus or new dump of the original pre-training data. However, this is very computationally inefficient, especially considering how large the initial pre-training corpuses are nowadays. Nowadays, it is more than 1 terabyte of data. And repeating that on like new dumps every single time is very inefficient, very expensive, because sometimes thousands of $1 million are spent on the pre-training alone. So secondly, we can think of continually pre-training the language model on just new data, such as recently crawled news articles or just brand new data. But this is known to result in forgetting of previous knowledge because the language model only sees new knowledge. In this paper, we try to address this problem using the second solution with continual learning methods in literature. So we propose a new problem setup called continual knowledge learning, where we take a pre-trained language model, T5 and GPT-2, which are frozen in 2019, which can perform different tasks in a zero-shot manner, such as slot filling, and can be fine-tuned to perform different knowledge-intensive downstream tasks. And we update the language model on a new recently crawled news articles between 2020 and 2021, to about 200,000 news articles. And we also propose a new benchmark that can be solved in a zero-shot manner, which requires probing the model for updated knowledge and just brand new knowledge. So there's some examples of the benchmark. So invariant llama is a variant of the original llama task, but we filtered only factual instances that should never change. So like iPod Touch is post-produced by. So these kind of information never change. Updated llama is factual instances that has changed from the original pre-training corpus. For example, the Prime Minister of England, it changed, and we made sure that these factual instances were in the original pre-training corpus and in the new corpus as well, but with changed information. And new llama consists of factual instances that were not in the original pre-training corpus, but only in the new corpus. And we also propose a metric that simply measures the trade-off between how much knowledge is forgotten in order to gain update and gain new knowledge. So this ratio, the lower the better. The lower the better the trade-off is. And we classify previous methods, continual learning methods for language models. And we find them in literature, and we classify them into the 3 categories, as in traditional continual learning categories. First is regularization, which aims to regularize during continued pre-training, try to regularize the weights so that it retains the original weight space. Second is rehearsal-based methods, which aim to mix in some of the original pre-training corpus, which might be pretty big, during continued pre-training on the new corpus. And the third is parametric expansion-based methods, which aim to freeze the original parameters and add new parameters during continued pre-training. So here are the main results. First, we measure the invariant llama and the updated llama and the new llama, and we measure the exact match score in a zero-shot manner. And we get the ratio of that, which the lower the better the trade-off. As you can see, the T5 initial model shows the highest performance in invariant llama, while showing the lowest performance in updated llama and new llama, because it retains all of the original knowledge while having no knowledge of updated and new llama. Sometimes it makes the correct answer, It's maybe a good educational guess. In the T5 vanilla, this is continual pre-training of the neural corpus without any continual learning methods, which results in the most amount of forgetting. However, it updates and gains new knowledge pretty well. When we apply previous continual learning methods for language models, results show that the methods are pretty effective at retaining the previous knowledge, while doing okay at updating and gaining new knowledge. There are 4 main findings in this paper. The first is that rehearsal-based methods perform the worst, which highlights the difference between previous continual learning setups and this continual knowledge learning setup. In previous continual learning setups, rehearsal-based methods used to show the best performance, and continual learning methods, new methods proposed to have efficient ways of doing rehearsal-based methods, like trying to limit the buffer size or proposing like very efficient rehearsal-based methods. However, in this setup, rehearsal-based methods, it's not really effective at retaining the original knowledge because the original knowledge itself is very big. It's like the original pre-training corpus is like 1 terabyte. So trying to mix in a subset of that during continued pre-training is not really effective at retaining the original knowledge. And if you want to do that, that's just the same thing as just pre-training on the entire new dump. So it's not effective, and it only hinders the updating and gaining of new knowledge. So this kind of highlights the difference between previous continual learning, which aims to continually learn like sequential tasks, while this is just a continual knowledge learning, which aims to gain world knowledge. And the second finding is that parameter expansion-based methods show the most robust performance, where freezing those parameters and adding new parameters results in the least amount of forgetting, while sometimes doing better updating and gaining new knowledge compared to the vanilla setting, and results in the best trade-off. The third finding is we try to identify what is the main cause of forgetting. So in this main setup, this is the main setup for the first table, which continually pre-trains the T5 model on the new corpus for 4 epochs. So it sees the data 4 times. We do have different variants, but just to highlight the main variant is small p1, which we limit the pre-training, the corpus size to 20 times smaller. However, we train for 8 epochs. So that results in 10 times less compute, so 10 times less training. But it results in a more degradation of performance in invariant llama. So it was trained 10 times less, but it resulted in more amount of forgetting. So we identified that the main cause of forgetting might be because in this setup, it sees the same data 8 times, which means that it has memorized the data. It is more better because more epochs means more memorizing, and that resulted in more forgetting. So there's a correlation between memorization and forgetting. Lastly, we show that these continual learning methods also are effective at retaining the performance on the original downstream tasks, to kill tasks that require the original pre-training data knowledge. And sometimes it even surpasses the original checkpoint. For future work, after we first did this work, we tried to aim to do specific knowledge deletion. So this work addressed knowledge update and knowledge gaining of the knowledge, but sometimes we require deleting specific knowledge from the language models. And we do have a recent draft on this called Knowledge and Learning for Mitigating Privacy Risk in Language Models in the archive. And the second future work was so how the knowledge update transfers to downstream tasks that needs the new knowledge. So in this setup, we just probed the knowledge downstream task for the previous knowledge, original knowledge, but how about the new knowledge? How does the language model integrate that very well? And it's still an unanswered question whether fine-grained knowledge editing or continual knowledge and continual pre-training works better for transferring that knowledge to the new downstream tasks. And the third is that we still need scalable methods of continual knowledge learning because parameter expansion method showed the most robust performance, but requires adding new parameters during each update, which might be computationally heavy, while if we scale the number of total updates. So that is still an open-ended question. Thank you for listening. And are there any questions?
Awesome. Thank you for the great talk. And yes, now if you have a question, please just unmute. Yes, Osman, you can start. Oh, that was a clap, sorry. But yes, if you have questions, please either raise your hand or just unmute and ask. I can get started. So I think given the time of when this paper came out, I think model editing was just starting. I believe it was the very same iClear 2022 or Chelsea Finn's paper came out, and since then there's like very large scale modeling and mass editing. So my question for you, I guess, is why CKL versus large scale model editing techniques like Rome?
So those model editing paradigm only deals with data that are like tuple data that are very fine-grained, and that also requires like human supervision, because humans need to identify the tuples. And also in that setup, like I mentioned in the first slides, it requires in this setup, it requires so those kind of benchmarks require they use X prime and Y prime. So that's also additional supervised data while trying to update X and Y to A. So that's further than the tuple. It needs more fine-grained data. So I think the continual knowledge learning is a much more scalable method of updating the language model.
Yeah, that makes sense. So you just have to add input large corpus of new data, whereas all those methods have very fine-grained, annotated, specific knowledge updates. Do we have any more questions from the audience?
One question I have is, were any of your facts or time variant facts sort of changing more rapidly than other facts? The current Prime Minister of England varies, at a time scale of years, but there may be things like weather that changes every day. So do you have any insight into that?
That is a very good question. I think, for example, like in this example, like Champions League or just other like, very like sport related stats that changes very rapidly in each game. But like Prime Minister, it changes every like 4 years. I guess that's a very interesting research question as well. So how to maybe like, depending on the facts, we can decide how to update the language model. But I think, yeah, in this paper we didn't really classify those instances into how often it is updated. But I think that's a very good question.
I have one question. So recently, OpenAI released the ChatGPT plugins, which uses a retriever to get information. Mm-hmm. So in your setup of continual knowledge learning, so do you think that that kind of methods could have benefit over continual pre-training?
I think that's a very good question. I think the plugins more rely on like retrieving new knowledge, so like knowledge that maybe like the language model doesn't know. I think in those setups, like plugins are definitely the way to go. But like for updated knowledge, so like when there's a knowledge conflict between the parameter knowledge and then like the external knowledge, then maybe in those cases it requires updating the knowledge.
I also have a question. Thanks for the great talk. I was wondering, like normally for us humans, the more we see something, the more we actually less forget, right? So our neurons get more, I don't know, used to that information, so we actually remember more. So why is it that the networks actually forget more because they see the data more?
So in this setup,
intuitive answer to that?
Yeah. So this setup, they forget the data more because the data that this sees was so that was like the 200 200,000 news articles. So it has a very distribution shift from the original pre-training data. It's much smaller and much more fine-grained data, I guess, because the original pre-training corpus is like a few, like millions of documents, not 200,000 documents. So when it memorizes the 200,000 news articles, then it does not, because it only sees the 200,000 news articles, so it does not see the original pre-training data. So it forgets about the original knowledge. Yeah. Hope that answers the question.
Okay, but if you were to combine
combine
those two data, then it would still work, I guess, as well.
Yeah,
but of course, it's much bigger data. It takes a longer time to train.
And so that's why we tried in mixed review. So we tried to mix in the original pre-training corpus during continued pre-training, but the results show that it's not really helpful in retaining the previous knowledge, and only hinders an update and gain of the knowledge. Maybe we can vary the ratio, but if we vary the ratio to include all the pre-training corpus, that's the same thing as pre-training from the new dump of the pre-training corpus. So that's very computationally heavy.
So is that a more fundamental limitation, that the total amount of data needed to update the model is more related to the scale of the model, and you can't really do continual learning unless you have that much data or some mix of new data and old data, right? So that seems to be a, like you're saying, you can't do continual learning if you have only 20,000 tokens and you're training T5.
Can you repeat the question again? I don't think I understand it correctly.
So given a particular model size, in order to achieve a fixed test set error, you need a large number of tokens. Whereas in this regime, you seem to be stuck with fundamentally having few tokens or few new data points.
I think having just few data points, that's not necessarily a big problem. The big problem is the original corpus that the language model gained the world knowledge is way too big to do like rehearsal.
Thank you.
Great. I think that's the last question, but if you can stick around, Joel, maybe we can ask some more after all have gone. Jiajie, the author of Ellie, do you want to go ahead and unmute and share your screen? Let's see.
Did you see me? Oh, okay.
Yes. Sorry. Great.
Wait a minute. Can you see the screen?
Yes.
Oh, yeah. Hello,
Great.
everyone. Oh,
I'll give you a quick intro. Yes, that'll be quick. Yes. Awesome. Well, we're in a treat now. After that, after Joel's talk, we'll now have Jiajie Zhang. He's an undergrad student, at Tsinghua Institute. His research interests are now tool learning of large language models and knowledge graphs. But I think this is especially a great treat because I don't think we've had an undergrad present at these before. So that is wonderful and outstanding for you. Congrats for that honor, and we are all in for a treat to hear about this talk.
Yeah.
So yeah, go ahead.
Hello, everyone. Today I will introduce our work and efficient lifelong pre-training for emerging data. Here's our motivation. As we know, most pre-trained language models are trained with static data, but in real-world scenario, streaming data from various sources may continuously grow, such as data from news, Wikipedia, or computer science paper. For example, if I have trained pre-trained language models on a Wikipedia dump and Tomorrow, I just got a dump of some computer science paper. So I want to pre-train the language models on this new dump, but I don't want it to forget the knowledge from Wikipedia. So this requires pre-trained language models to integrate the information from all the sources in a lifelong manner. So our question is, how can we efficiently pre-train language models in a lifelong manner? Here's two challenges for efficient lifelong pre-training. The first is efficient knowledge growth, which means that with the data scale growing, packing more knowledge into a fixed size pre-trained language models becomes increasingly hard. The second is that we need proper knowledge stimulation. That is, during pre-training, various knowledge from all domains is packed into the pre-trained language models hastily. However, a certain downstream tasks may largely require the knowledge from a specific domain. To address these two challenges, we propose AI, targeting at efficient lifelong pre-training for emerging data. Here is our overall framework. Our framework is mainly based on function preserve model expansion, that is, flexibly expand an existing pre-trained language models wides and deeps to improve the efficiency of knowledge acquisition. Specifically, when data DI from a new source come in, we first expand the old model that is MI-1, its widths and the deeps by recycling its weights, then use a subset of previous data, which is also called memory, to rapidly recover the performance of the expanded model. Then we continue to train the model on DI, the new data DI mixed with data from the memory to prevent catastrophic forgetting on the previously learned knowledge. Here are some details of widths and deeps expansion. For widths expansion, we randomly select several columns of the weight matrix and replicate them, dividing by the number of replications. In this way, we can ensure that the layer has almost the same output given the same input before and after the widths expansion. For deeps expansion, we randomly select several layers from MI-1, copy each layer's parameters and insert the replication layer right after the original layer. We found empirically that inserting the copied layer into other position, like we inserting the replication of the layer 1 after the layer 4, would cause a performance drop. And the reason is that it will violate the processing order of the original layer sequence and break the model's original functionality. Besides function preserved model expansion, we also adopt pre-trained domain prompts to disentangle the versatile knowledge learned during pre-training, and we can stimulate the proper knowledge for downstream tasks. Specifically, during pre-training, to disentangle the knowledge from different sources, we implant a soft prompt token into the input to prime the pre-trained language models which kind of knowledge it is learning. During the fine-tuning, when applying the pre-trained language models on a similar domain of data seen before, we could leverage the trained domain prompt and prepend it before the input of downstream tasks. In this way, we manually manipulate the pre-trained language models to stimulate the most relevant knowledge learned during pre-training. This is our experiments. We pre-train two kinds of model, Roberta and GPT, on 5 sequential domains data, including Wikipedia, news, reviews, and biomedical and computer science, and keeps the training time to be the same for all the baselines. For pre-training, we propose 2 metrics to evaluate how pre-trained language models performance on the learned domains. The first is average perplexity, which measures the average performance on all the same data. Lower average perplexity indicates that the pre-trained models generally learn more knowledge from existing domains, while the average increased complexity just measures the influence of current data DJ on previous data. Lower average increased complexity means that these pre-trained models forget less knowledge learned before. For fine-tuning, we just use the downstream performance of the final model, that is have pre-trained on the all 5 domains on each domain as the metric. Here's the result for pre-training. We can observe that compared with all the baselines, including the EWC and the MAS and AGM, which is a regularization-based method, and the ER, which is just naive reuse the memory, and the logic KD is the knowledge destination, which just makes the distance from the last model and this model's last layers features close, and the PNN, which is also a method that expands the model's weight. We can see that compared with all these baselines, our method achieves the lowest AP and satisfying AP plus after finishing training on each domain. This demonstrates that given limited computational resources, any could acquire more knowledge and in the meantime, mitigate the knowledge forgetting problem. And here is a graph of AP and AP plus over training time. We can observe that the AP of Allen decays the fastest, which is the gray one, and this showing the superior training efficiency of any overall baselines. After pre-training the model on all the 5 domain of source data, we just fine-tune them on 5 downstream tasks, 1 for each domain. Here's some result. We can see that Allen performs the best on all downstream tasks, indicating that the knowledge learned during pre-training could be properly stimulated and leveraged for each downstream task. Yeah, that's all. Thanks. Welcome any questions.
Great. Thank you very much. And yes, now if anybody has questions, please, same as last time, unmute, raise your hand, go forth. I just have a general question in terms of growing models for continual learning. And thank you again for that talk. Do you think, so I guess in your perspective, do you think there's some like fixed max underlying capacity, like some maximum point where you can't grow the model anymore? Instead, you need to like start from scratch and retrain from scratch?
I think that when the model is really large, you can just train it from scratch. But there's some problem because such as the initialization. We found that if you can train a smaller model from the beginning and then recycling its parameter, that so this issue may be solved better. But we also found that if you have a really good initialization method, that's not a problem. Yeah.
Actually, sorry, I want to interrupt, but actually, researchers from Huawei in China, they have tried that this model expansion technique has been tested on like models with 100 billion parameters, and they find that this method still works. But I don't know whether this method will still work on even larger models. But 100 billion, I think it is large enough.
Is this Yujia? Is this the other author?
It's me, Yujia.
Okay. This is the other co-first author for those. Nice to meet you.
Hi, nice to meet you too.
Great. So you're saying the work has actually been tested by others and very large scale. Awesome. Do we have any more audience questions on this? Can you check the chat? Let's see. Okay. There's two questions. The first question is, this is from Song Yun Yun. Does growing the number of parameters, the width and depth, does this increase the inference and train time of the model? So how does the increase in size affect the inference and train time?
In our experiments, we just keep that all the baselines train the same time on each domain. Sure that if you expand the model, the inference time will be longer, but the large model also has a better ability to memorize thin data, and it can learn faster than small data. So we think that expanding the model is somehow better method.
And one more question from here, and then we'll go to you, Aswin. But could you share some insights about the appropriate number of parameters needed for a fixed size of knowledge? I guess the question is larger always better?
You know that from the GPT-3, we can see that actually like 100 and hundreds of billions model has the ability to memorize almost many things, but it can also fails to memorize some long tail entities knowledge. So we think that besides expanding the model, we also need some more high-level ideas to solve the fundamental limitation of the language models. Yeah.
Yes, and I want to say something more. This is actually we did not investigate how at which step we should expand the model and how much we should scale it. But I think it is really an important research direction to explore in the future. And I think recently OpenAI just released their newest technique, predictable scaling. I think this is very related to this topic. Maybe we can draw insights from this predictable scaling to understand how much we should expand the model size.
Great. Aswin, did you have a question still?
Yeah, if you have time.
Yes, we have time for one more.
So I was wondering about the sequential domains here, and one question was, did your AP average over sort of different presentations of these domains, order of presentation, and also does the size growth somehow affected by the order? Like maybe some of these domains are harder than other domains, and do they blow up the size immediately? Like, do you have any insight about that?
This is a good question, and we have experiment for many orders of these 5 domains. We just observe that the similar result as that in my slides. So, but we also think that the sequential of the domain is somehow important. I think that if you train a totally unsimilar domain, after you if you continue to train on a totally unsimilar domains, it will forget him more. So but we don't have much insight in this paper. I think this is a good question for future study. Yeah.
Okay, does that answer enough, Ashwin?
Yeah, thank you.
Mm.
Okay, I think at this point we'll move on to our last speaker. So thank you
Yeah.
again for that great talk. And please, if you have time to stick around, we'd like to talk a little more after. But Zixuan, if you are here, you can go ahead and start sharing your screen.
Can you see my screen now?
Yes. And it's not full screen yet. Okay.
Is it full screen now? Okay.
Yes. I'll give you a quick intro. So this is our last speaker for today, Zixuan Ken. Zixuan is a fourth-year PhD student at the University of Illinois, Chicago, under the guidance of very distinguished Professor Bing Liu. He's published 15 plus papers at top conferences, ICLEAR, such as this one, NeurIPS, ACL, EMNLP, etc. His code has earned lots of stars on GitHub, 200 plus stars, 50 plus forks. Additionally, he has been interns at Meta AI, Amazon Science, and Tencent AI Lab. And his research interests are broadly focused on machine learning and natural language processing. And in terms of fundamental research, Zixuan's work is centered around continual and lifelong learning, which is, of course, why we have invited him here today to talk. In the realm of applied research, he's even focused on very large language modeling. Very happy to have you here today and looking forward to your talk.
Thanks. So thank you for the invitation. Thank you for the introductions. My name is Zixuan, and I'm happy to introduce our work, continual pre-training of language models, and the code and data are publicly available. So basically, let me, next page. Okay. So basically we have heard many motivations. So I just talk about that very briefly. So basically existing language models, even though the largest one, once they trained, they are fixed. However, in the real world, the data shift constantly and new domains, events, or topic, they keep emerging. So this basically requires the language model to be updated to serve the user better. So our focus in this work is to continually learning or updating or pre-training a language model using a sequence of domain corpora, which we call continual domain adaptive pre-training. And the domain here is simply an emerging or specialized event or topic. So as a concrete example, given a pre-trained language model, so in this work, we focus on this kind of further pre-training or post-training. But of course, this technique can also use it if you want to train the language model from scratch. But in this work, we assume we given a pre-trained language model, we download a pre-trained language model from the internet, and we continually pre-train it using a sequence of domains. For example, the first is restaurant, the second is phone, the third one is camera. And typically in NLP, these domains are unsupervised or self-supervised, and they have a large amount. So in the left-hand side, we wrote a transformer diagram with on top the mask language model head. And after the continued pre-training, we evaluate the continued learning performance using n tasks. And each n task corresponding to one domain and will have its own training and testing set, and it's trained individually, and it will not affect the domain adaptive pre-training. So this basically tells us the difference between conventional continual learning and the continual pre-training, because in conventional continual learning, each task is an n task. You use the task testing performance to evaluate the continual learning. But now the continual learning happened in the domain adaptive pre-training stage, and we use n task fine-tuning performance to evaluate the continual learning. And for example, we use sentiment classification as our n task. We have sentiment classification for restaurant domain, for phone domain, and camera domain, and their individual performance will be used as the evaluation for the continual learning systems. And in our work, we basically have 6 domains, and correspondingly, we have 6 n tasks. So we can see this 6 domain is all around like 1G. And for the domain, we have sentiment, for the n task, we have sentiment classification, we have relation classification, and so on. They have their own training and testing set. They are supervised, so they have a different number of classes. So yeah, so basically, in summary, our setting is to continue pre-training a sequence of domains. And just as other continual learning system, we assume we do not have access to the previously learned domain data. And we also assume we do not have access to the original pre-training data, because we assume we download a pre-trained one, we would not have the data that used to pre-train the language model. And during the end-task fine-tuning stage, we assume we do not know the domain belonging. So we will not keep domain ID when we do the end-task fine-tuning. And our goals are twofold. One is to prevent forgetting. The other one is to facilitate knowledge transfer, including backward and forward knowledge transfer. And our approach is called Continual Domain Adaptive Pre-training of Language Model with Soft Masking, or DAS in short. So now we can talk about a bit more detail about our techniques. So the key ideas of our technique is that we first detect the importance of unit for two types of knowledge, general knowledge and domain knowledge. And then we soft mask those important units when we train the new domain. And these two can actually help us prevent forgetting and also allow knowledge transfer. So some key challenges here are, how do we detect the importance for the two types of knowledge, and how do we achieve soft masking? So we start from a pre-trained language model. We first go to the importance computation components. So in this component, we want to compute the importance. The reason is that first, we know not all the units are important, just like it shows in the pruning community. And also, if we can compute the importance, we can protect them afterward. And one thing to know is that no training involved in this component yet. We only want to compute the importance. So, so basically, we use the gradient to indicate the importance. So when we talk about gradient, we need loss and we need units. So in the loss, we call it LIMT, the loss for the importance. For domain knowledge, because we have its data up when we train it, so we directly use the mask language model loss as the loss for the importance computation. And we also add a virtual parameters GL. So basically, each virtual parameters GLI in GL corresponding to either an attention head or neurons. Or so basically, we use this virtual parameter because there are different type of layer in transformer. We want to unify them. So later on, we can just compute the gradient of this LIMT with respect to GL. Then we can know the importance. So we basically compute the gradient of each samples, and then we average over all samples, and we use the absolute gradient to indicate the importance. This is straightforward and has been widely used in the pruning community. But when it comes to the general knowledge or pre-trained knowledge, we need to be more careful because we do not have the data, so we cannot do the same thing in when we compute the importance for general knowledge. So what we do is that we leverage the random dropout in the standard transformer, because random dropout introduces random noise, and given the same input, the difference between the representation indicate robustness. And those units that are important to the robustness is likely to be important to the pre-trained knowledge or general knowledge as well, because its change will cause the pre-trained language model change a great deal. So we basically use the robustness as the proxy to compute the importance. And based on these intuitions, we propose a new LIMT based on the KL divergence to compare the two representations from the same input. So one thing to know is that we only do that for X1 for the first domain, because we want to compute the pre-trained general knowledge importance. And after the first domain, the transformer has different kind of knowledge. It's not only the pre-trained knowledge. So we only do that to pre-train, to compute the importance of units for the general knowledge or pre-trained knowledge. With this new LIMT, we can do the same thing as what we do for domain knowledge. We just again use the absolute gradient to indicate the importance. So this is basically how we compute the importance. And after this importance computation, we will get a set of importance, including the importance of unit for general knowledge and for all the previously learned domain knowledge. So these are all the ILK, the set of importance. And given this set of importance, we go to do the soft masking. And the goal of the soft masking component is to soft mask the gradient based on the set of importance we have. We want to do that because we want to protect the important units when we train the new domain. And we also want to allow some type of knowledge transfer. So here is how we achieve that. So what we do is we first normalize all the importance so that they are comparable, use the 10-ish, and then we accumulate the importance because they are already normalized. So we can directly use element-wise maximize to accumulate those importance. And lastly, we convert the importance to mask by doing the 1 minus importance. And then we element-wise multiply this importance to the gradient. So the thing to know is that these soft masks only happen in the backward pass. So we do not do anything in the forward pass. So that basically means the forward transfer is still possible. And also this importance after normalization is within 1 and 0, but it is not hard. It's not 0 or 1. It's within 1 and 0. It's a real number. So it's still adjustable if the knowledge really needed to change. So backward transfer is still possible. So by doing this, we are allowing backward transfer and we are also allowing forward transfer. And those important units, they are also protected because we are doing soft masking on them. So this is the key idea of our technique. And after this soft masking, we can go to the next task or next domain. We again compute the importance, and this set of importance now have one more importance score, and then soft masking again. And then this whole thing is how we do the continual pre-training. So overall, our techniques figure can be seen here. So first, for the first domain, we first compute the importance of units for general knowledge using this KL divergence as our LIMT. And the gradients here will be used to compute the importance, but it will not use to update the transformer layer yet. We just want to compute the importance. And after the initialization, we start the continual learning. So in forward pass, we do nothing, but in backward pass, we normalize the importance element-wise to accumulate, and then convert it to mask, and then soft mask the gradient. And after this soft masking training, we compute the importance for that specific current task again, and then this importance will be used in the next task training. So the continual learning can go on with this soft masking technique. So, and then here we can see the result page. So basically the first row is Roberta, and we have column for restaurant, ACL, these are our domains. We have average, we have forgetting rate. So forgetting rate, record forgetting rate is if you have a positive forgetting rate, that means you have forgetting. So forgetting rate is the smaller, the better. And the first row, Roberta, meaning that we do not do any pre-training and we test on each domain individually. So this is non-continual learning setting. And we have DAPT Roberta. That means we do pre-training individually for each domain because it's still non-continual learning category. And we test on the end task result. So basically we can see without pre-training, average is 73. And with pre-training, DAPT Roberta, the second row is 76. So with pre-training is better, which is not surprising. Many papers have been shown that. And our technique DAS is 77, which can do even better than individual pre-training because we can achieve forgetting prevention and also knowledge transfer. And we can also see in the continual learning category, we have NCL, which is naive continual learning, meaning that we do nothing or we do nothing special on continual learning. We're just sequentially pre-training these 6 domains. And we can see its forgetting rate is positive. That means it does has forgetting. And our forgetting rate is negative. That means we does have a positive backward transfer. So, and then we also compare with popular continual learning baseline, for example, regularization-based method like EWC, distillation, and replay-based method at DER++. And we can see they are all worse. And basically this is I heard that the same observation in Zhang that the replay method is doing worse in this continual pre-training setting. And we also compare with parameter isolation method, like the HAT, is actually also getting worse. Basically, that's because when we do parameter isolation, that means we need to isolate the parameter in the transformer. So the end task cannot use the full language model. So in them, the end task will perform worse naturally. So basically, that means we need the full language model to be used when we do this domain adaptive pre-training. There are also other methods that try to perform both knowledge transfer and forgetting prevention, like DMix, BCL, Classic. And in fact, they're all worse than DAS because they're not specifically for the continual pre-training. So yeah, that's pretty much the results. And the key takeaway here is that we studied the problem of continual pre-training of language model. We try to incrementally accumulate knowledge to the language model by computing the importance of units for two types of knowledge with different LIMs. And then we soft mask only the backward propagation, not the forward pass, based on the importance, which can help the forgetting prevention and knowledge transfer. So yeah, lastly, we will have an in-person poster at ICLR next week. If you happen to be there, you're welcome to stop by. And also the code and data are publicly available. Feel free to check them out. We have benchmarked the continued end-task learning and also continued domain adaptive pre-training. Yeah, I think that's it. Thank you.
Outstanding. Great. I guess it's question time. So if you have questions, again, please unmute, raise your hand wherever you want to go. I'll go ahead and start with one. So I apologize if I misunderstood something, but how do you balance, I guess, the masking of the general knowledge versus the task specific? Is it like emphasized with a higher rate or some higher ratio, or is it equal?
Basically, it's equal. I accumulate them equally using this element-wise max. So okay. I didn't differentiate them when accumulating. Yeah.
And kind of going off of that, do you know, did you have any way to compare, I guess, how good your method of using dropout was compared to some, like, I guess, cheating upper bound where you did some type of masking on some general knowledge corpus? Do you have any way to like know how far off your dropout estimate is compared to, you know, some potential larger, better way to do that?
So I think one upper bound is to pull all the 6 domain data all together and pre-training on this large data to see whether our method is getting close to that. And we actually have this result in our paper, and it's actually the average end task performance is also 77. So actually we are basically achieving the same thing as we pull all the data together to do that. Yeah.
That's outstanding. That seems like a very ingenious method. Good job.
Thank you.
Hey, I have a question. Great talk, by the way. It's really fantastic. I was wondering, so this is on task-oriented dialogue, right? Task-oriented interactions. How would your results, do you think, would apply to open domain dialogue, for instance, like for long-term interactions to learn data over time?
So this is for domain pre-training. You're talking about dialogue.
Yeah.
So in our data in this work, I think we do not deal with dialogue. So your question is whether this can use in dialogue domain or
yeah, if it would actually apply.
So
for open domain knowledge, not just dialogue, for open domain knowledge of memories, for instance.
I think this should help in preserving some knowledge. If you mask some part of the transformer, naturally it should help preserve knowledge, either it's dialogue or not dialogue. So I think it should still be helpful, I guess.
All right, thank you. I might try it. Thank you.
Thank you.
Any more questions? I'll repeat a question I actually asked an earlier speaker. Where do you think the plasticity ends? How many domains do you think you could learn until the masking comes to the point where you're masking too much and you can't effectively learn?
Yeah, I think this is actually another advantage of doing soft mask, because if you do hard mask like HAT, like these things, the mask will consume very quickly. So I actually looked at HAT and I found, oh, after just 2-3 tasks, these neurons are consumed very quickly. But now we do soft mask, so it's consuming much slower. But I believe, yeah, you're right. At some point, we will hit the limit, and we may need to expand at some point. But I would say the soft mask, this limit will be much slower than those hard mask method, than those many parameter isolation methods.
That's a great answer. Someone asked me this recently about continual learning, and the answer I gave them was train a new model. Like, you can't. You can get model 1.1, 1.15, 1.2, but eventually, at some point you may just have to train model 2.0.
True.
Yeah. Great. I think this will be a good chance for us to go ahead and wrap up the seminar. So thank you, everyone. Thank you all the wonderful speakers for today. I thought this was a very insightful seminar, and I'm sure we'll have many views later on YouTube. Yeah, I think at this point we will turn off the recording. Anyone who wants to stick around and just have some general talk, please do. If not, thank you for attending. We'll see you next month.